All right, thank you so much. Well, first I would like to thank the organizers for having me speak here. My talk today will be mostly based on this paper with two excellent MIT students, Arko Chatterjee and Sal Pace. And Sal is here in the audience too. I will also talk about a second paper we wrote in December with Sal and Arko. And let's get started. So the paper and the talk will be about lattice chiral symmetry. And I have to say, I think Sal, Arko, and I were really outsider of this field. And I'm really honored to have the opportunity to talk about our work, to this audience of experts on lattice chiral symmetry. So any opinions or comments will be highly valued. We're really curious to see how you guys think about it. All right, so I'm going to give you our take on this problem. So to this audience, so in recent years, we have seen a lot of developments on understanding global symmetries and their generalization, both in continuum quantum field theory and in lattice system. Now, the question that motivated us to think about lattice chiral symmetry is that given all this development on generalized global symmetry, can we leverage this new advancement to gain some new insights in lattice chiral symmetry? And David gave a beautiful review talk on lattice chiral symmetry with a lot of new progresses. So the main question we would like to ask or approach in this talk is, given a continuum quantum field theory, this is my target, can I realize its chiral global symmetry and possibly their two Hoof anomalies on the lattice? So let me emphasize that all the example I'm going to talk about today, the quantum field theory is non-chiral, but I'm interested in the chiral global symmetry of this non-chiral quantum field theory. All right. So what would be the simplest setup to even ask this question? So we want to talk about QFT. So let's go down to the lowest possible space-time dimension. That's 1+1d. And of course, the simplest theory will be just a free massless Dirac fermion, 1+1d. A Dirac fermion in 1+1d has two components, psi left and psi right. Psi left is a one component, complex, left-moving biofermion. Psi right is a one-component, complex, right-moving biofermion. In terms of psi left and psi right, they are all one component. I'm not hiding any indices. And this is the Lagrangian. And every one of us must have seen this Lagrangian at least once in our life. And since the left movers doesn't talk to the right movers at all, we have two U1 symmetries. The first one is a vector U1 that rotates the left mover and the right movers by the same phase. The second one is the more interesting one. It's an axial U1 that rotates the left mover and the right mover by the opposite phase. So the emphasis should be put on this plus sign. Now, of course, by this point, you might be wondering, why don't I organize the symmetry in a slightly different way? I can write it as U1 left times U1 right. Why do I have to write it in a vector times axial way? Well, the reason for that will become clear momentarily when we go to the lattice. And because we work with the vector and axial basis, one fun fact is that if you take theta to be pi, then the pi rotation of the vector symmetry coincides with the pi rotation of the axial symmetry. So that's just saying that globally the group is actually U1 vector times U1a with a Z2 quotient. Now don't worry too much about the Z2 quotient. It's not terribly important for the rest of the talk, but it's a good practice to keep track of the global quotient. All right, so this is the continuum theory. This is our target. And this is our target quantum field theory, and these are the two target global symmetries that we want to realize on a lattice. So in this talk, I'm going to work with the Hamiltonian lattice formalism. So my space, again, will be a discrete one-dimensional periodic spin chain. Time, on the other hand, is continuous. I'm going to assume the number of lattice size L to be even. Now, of course, the most naive thing you would like to do is, given that the continuum Dirac fermion has two components, naively you would just put two complex fermions on every site. But as everyone in this room know, that there's a famous fermion doubling problem. It's just saying that the naive dispersion relation, the linear dispersion relation in the continuum, when you regularize it on the lattice, it has to be a periodic function as you go across the Brillouin zone. So on this end, you get a nice right-moving fermion, but inevitably on the other end, you get a left-moving fermion. So if you put two complex fermions per site, you will get twice as many Dirac fermions in the continuum limit as you will hope so. Now, the way to fix this issue in 1+1d is very simple. You get a factor of 2 from the fermion doubling problem, so you just have to multiply the whole problem by a factor of 1/2. So instead of putting two complex fermions every site, what you do is to put one complex fermion per site. And I'm going to denote it by Cj. So Cj and Cj dagger, they obey the standard anti-commutation relation. And when you quantize it, on every site, you get 1 qubit. So you have a two-dimensional Hilbert space per site. And the total Hilbert space is 2 to the L dimensional. It's a finite-dimensional Hilbert space for finite L. Now, the Hamiltonian I'm going to work with is really the simplest possible lattice Hamiltonian that was also studied by Tom Banks, John Koga, Lenny Susskind from 75 to 77. And that's this Hamiltonian. All right, so this is really the simplest Hamiltonian you can write down: nearest neighbor interaction, C dagger C, so that it will preserve one U1, as I will discuss momentarily. The continuum limit of this Hamiltonian is a single, free, massless, non-chiral Dirac fermion. All right. Okay, so we have a Hamiltonian that flows to our target quantum field theory. Now we have to ask, does this Hamiltonian have the chiral global symmetries that we want to have? So let's take a look at this Hamiltonian. Well, obviously, there's a U1 symmetry on this lattice that just rotates the complex fermion by an overall phase. That's a manifest U1 symmetry, which you can identify as the vector U1 in the continuum limit. I'm going to denote it by U1v. Oh, yes, Lance.
I thought we weren't supposed to use arrows.
It's a new day, new rule. Thanks for the question. Any other insightful question? Great. All right. So that's one of the two U1s that you want to have on the lattice. But you see, here's the problem. Previously, we wanted to avoid the fermion doubling problem by putting a single complex fermion per site. In a different choice of the gamma matrices, you can think about putting one component of the Dirac fermion on the even side and the other component of the Dirac fermion on the odd side. This picture was already explained in Silvio and Ross' talk earlier in this conference. In the continuum, the two component Dirac fermions live at the same space-time point. So you can rotate them vectorially or axially, it doesn't matter. But on the lattice, because we sprinkle them on the even versus the odd side, that will make one of the two U1s obscure. So the central question we want to ask is, where's the axial U1 symmetry in this simple staggered fermion Hamiltonian model? Of course, the question could just be that the axial U1 is not there on the lattice. Right? Symmetries can emerge in the continuum every day. But is that really the case in this particular Hamiltonian? All right. Now, common law states that it's difficult to realize an axial U1 global symmetry on the lattice because of an anomaly between the vector U1 and the axial U1. Now, this anomaly is really, I think, it's one of the first anomalies understood by mankind, and that's the Schwinger anomaly. Schwinger anomaly states that if you start with a free Dirac fermion in the continuum field theory, you have U1 vector times U1 axial global symmetry. Both of them are honest to God global symmetries. However, if you gauge the vector global symmetry to go to QED, then the axial global symmetry is broken quantum mechanically. This is a 1+1d counterpart of the AVJ anomaly. In equations, it means that in QED, where the vector symmetry is gauged, the axial nurse occurrence is no longer conserved. This was first alluded to in the 59 paper by Schringer, but in my opinion, it was really stated clearly in this paper by Ken Johnson in 63. And this is the one loop two-point diagram that captures the Schringer anomaly. This kind of perturbative anomaly, by perturbative anomalies, I mean anomalies that can be captured by perturbative Feynman diagram, are particularly challenging to realize on the lattice, especially with the finite-dimensional local Hilbert spaces, which is our case here. You know, in our lattice setup, we have a qubit on every side. For finite L, it's a finite-dimensional Hilbert space. Having said that, this anomaly has been realized on lattices where the local Hilbert space is infinite-dimensional. And these days, such a class of lattice model goes under the name of the modified Villain model. This is a Euclidean lattice model, which is to be contrasted with the Minkowski/Hamiltonian lattice model that I'm discussing today. So this went back to works by David and Igor back in the 90s, and recently there was some generalization of that in the context of Euclidean lattice model. Even more recently, the modified Villain formalism has been applied to Hamiltonian lattice model as well. But all these models involve infinite-dimensional Hilbert space on every local site. And that's not the case for us. All right. So this is another reason why people typically think it's difficult to realize such a perturbative anomaly on a lattice model with finite-dimensional Hilbert space. So in this talk, we are going to offer a slightly different perspective on the axial symmetry in this simple Hamiltonian lattice model. We're going to find both the vector and the axial global symmetry exactly in this lattice model. And what do I mean by that? I'm going to write down an explicit operator that acts on this 2 to the L dimensional Hilbert space. One of them is QV, which I already did. The other is Q axial. Both of them commute with the Hamiltonian for finite L. And therefore, I want to call them symmetries. Both of them have integer eigenvalues. So they really generate, when you exponentiate them, they generate a compact U1 global symmetry. This is to be contrasted with the R global symmetry or R gauge theory that Thomas discussed in his talk. So this all sounds nice and rosy, but there's always a catch in theoretical physics. And here the catch is that these two charges do not commute on a finite lattice. And we'll see why that is important later on. All right, so that's the punchline. And now let me get into the details on how to derive this axial charge. Any question at this point? Great. Yeah, yes?
Do you have like the commutator going to 0 as L goes to infinity?
Excellent, yes. And I will talk about that later on. Indeed, this commutator goes to 0 as you take the thermodynamic limit. So everything matches with the continuum in the thermodynamic limit. But on a finite lattice, they do not commute. Okay, I will talk about anomaly in a little bit. In the continuum, yes. But yeah, on the lattice, it's more subtle. And I will talk about that down the road. Yes. Can you say again? Sorry? I will talk about that too. Yeah. They will come. Don't worry. All right. So let's proceed. Now this might be some of the more technical slides of the talk. So let's go back to the continuum for a minute. We have this two U1 vector and U1 axial. This is the way they act on the fermions. One very simple observation that will be crucial for the rest of the construction is that the vector symmetry and the axial symmetry in 1+1d free Dirac fermion theory are related by conjugation of a charge conjugation symmetry. So this CR is a symmetry that takes the right moving vial fermion to its dagger. So why is this true? Let's look at the transformation rule of the vector and the axial symmetry on the left moving fermions and the right moving fermion. The only difference is this minus sign versus the plus sign for the right movers. So if you conjugate the vector charged by the CR operator, you exchange what you mean by psi right with psi right dagger, and therefore exchanging the plus with the minus up there. Okay, just a simple group theoretic fact. All right. Now, given that we already have the vector charge on the lattice, it suffices for us to realize this right-moving charge conjugation symmetry on the lattice. Once we have that, we apply this formula, and we are all set. But the question is how? How do we find the lattice counterpart for this charge conjugation symmetry? You're asking about the mass term?
Mass term, left, right.
Sorry, say again?
Mass term, which is left, right, still would be okay. This is...
The mass term will generically break. I will talk about various deformation you can add. Most of them will break the symmetry, some of them will preserve the symmetry, so just hold on to that thought. Okay, so the question is, how do we realize this charge conjugation symmetry on the lattice? Now, throughout the entire talk, we only have one trick, really just one trick. The trick is to be real. So what is this trick? So you see, so on the lattice, we want to decompose every complex fermion in terms of a pair of real fermions. If you think about it, it's kind of funny because I don't know about you guys, but when I first learned math, I first learned real numbers and then move on to the complex number. But when I learned fermions, we always first learn Dirac fermions, and then we move on to learn the Majorana fermions. Of course, there's a good reason behind. But here in this talk, it's really crucial to think about every fermion, both on the lattice and in the continuum, in terms of the minimal representation of the Clifford algebra. Okay, so on the lattice, we're going to do this decomposition, and of course, we were not the first one in the history of physics to do so. This is highly inspired by Kitaev's seminal work for the Majorana chain. If you decompose the lattice complex fermions into a pair of real fermions, then the Hamiltonian factorizes into two decoupled Majorana fermions. In the continuum limit, this real lattice fermion Hj will go to a left-moving Majorana vial fermion A left and a right-moving Majorana fermion A right. Similarly, the real B fermions go to a pair of left-moving and right-moving fermion. It's important that a single real fermions give you a pair of left-moving and right-moving fermion because of the fermion doubling aspect. All right. As we said in the previous slide, what we want to find is a lattice operator such that when you take the continuum limit, it becomes a symmetry that flips the sign, that takes psi right to psi right dagger. Written in terms of the real fermion notation, that means that you want to find the symmetry that flips the sign of a single right-moving Majorana vial fermion. Okay, so what would be the symmetry that does the job? By this point, it should be relatively obvious to people who have thought about lattice fermions. And that's going to be the translation operator, the lattice translation operator. So let's take a look at the Hamiltonian, written in terms of the real fermions. Since they decouple, for the moment, let's forget about the A fermions and focus on the B fermions. This is the dispersion relation. The energy is just a sign function of K. On this end of the brilliant zone, near k equals to 0, you'll get a bunch of left movers. So some people might be wondering, why do I call this left mover? It looks really like a right mover. But this is really because of some inessential sign convention that we pick. But believe us, in the paper, we really got every convention straight. I think Sal, Arco, and I would spend 3 hours trying to sort out the left and the right. And in the process, we realized that Pochinski actually used a very confusing convention for the left mover versus the right mover. But anyway, don't worry about the fact that we call this left mover and that right mover. Everything is consistent at the end of the day. So on this end of the brilliant zone, you get a left mover, B left fermion. On the other end, you get a B right mover. So the hero of the story is this Majorana lattice translation operator. Since we only focus on the B fermion, we want to talk about an operator that shifts the B fermion by one side, but leaving the A fermion as is. This is to be contrasted with the lattice translation that move both the A fermion and the B fermion by one side. This symmetry has already been discussed many times in the literature, starting from Lenny's paper back in the 70s. But this operator TB is more obscure when you write everything in terms of the complex fermion. And this is an advantage of working with the minimal representation of the fermions. So why do I want to look at this Majorana lattice translation operator TB? So in position space, it shifts the B fermion by one side. In momentum space, lattice translation is diagonalized. So it picks up a phase that depends on the momentum. Now this phase is roughly 1 when you're at this end of the Brillouin zone, and it's roughly -1 when you're at the other end of the Brillouin zone. And therefore, this lattice translation operator that only shifts the real B fermion is the guy we are after. This is the operator, this is the lattice operator that as you take the continuum limit, that becomes the right-moving charge conjugation symmetry, which flips the sign of a single Majorana Weyl fermion. Okay. So we found the symmetries, TB, that goes to the charge conjugation symmetry. So the next thing we need to do is to follow the continuum relation and conjugate our lattice vector charge by TB and see what we get. If you write out QB in terms of the real fermion notation, it's a sum over AJ, BJ, and you apply this lattice translation on it, you don't move the A, but you shift the B fermion by one side. And this, I claim, is the axial charge on the lattice. So now we have the answer. Let's try to see what's nice about this operator QA. First of all, I claim this flows to the continuum axial charge as you take the thermodynamic limit. The reason is because this Majorana lattice translation operator TB flows to this charge conjugation symmetry in the continuum limit. And QV just goes to QV. And therefore, this QA will become the axial charge in the continuum limit. And let me itemize the nice properties of this axial charge. Since it's made out of the Majorana lattice translation and the vector charge, both the Majorana lattice translation and the vector charge commute with the Hamiltonian. Their composite, this QA, also commutes with the Hamiltonian. So this is the exact global symmetries of your Hamiltonian, of your lattice system. Second, since QA is related to QB by conjugation, unitary transformation does not change the spectrum of the eigenvalues of your operator. And given that QV has integer eigenvalues, this QA also have integer eigenvalue. So it generates a compact U1 global symmetry, an exact U1 global symmetry on the lattice. Third, this QA is the sum of local terms on the lattice. It's not entirely on-site, right? So this fermion AJ talks to its nearest neighbor, BJ plus 1, but it's still local. You know, one-side difference as you take the thermodynamic limit is nothing. So you not only have the notion of a conserved charge, you also have a notion of the time component of the Noether current on this lattice. Related to this fact, when you exponentiate this QA charge, you get a unitary operator, as Wigner would prefer, and it acts very nicely on the local fermions of your lattice model. It acts on A and B almost like a SO2 rotation, except for the fact that it shifts the fermions to its nearest neighbor. But still, one-side difference on the lattice in the thermodynamic is nothing, and this is really a locally acting U1 global symmetry. Yes.
You find this translation operator with the charge conjugation operator on the right moving, right?
Yes.
But the charge conjugation operator is order 2 operator.
Very good. I'll come back to that. Excellent question. Hold on to that thought. All right. Great. But the price you pay is that they don't commute on the lattice. In contrast, their continuum counterparts do commute in the continuum. In the continuum, it's just phase rotations, and phases commute with each other. Well, whenever you have something that don't commute, and both of them are symmetries of your Hamiltonian, you should ask, what kind of algebra do they form? Right? Someone hands you an SU2 algebra, U1x and U1y, you take the commutator, you get U1z, and you close the Lie algebra. What do we have in this case?
You cannot equate.
Can I take what?
You cannot equate to
In the continuum, they commute, so they're commutative. There's a problem if you look at the local Noether current, that's the Schwinger term, but I'm talking about the entire charge. Okay? On the lattice, even the entire charge don't commute. Right? So what do they generate as you take this commutator between QB and QA? It turns out that they generate a very large algebra. So let me define these two operators. Qn is defined similarly to QB and QA. In fact, Q0 is QB, Q1 is QA. And this Gn is some quadratic stuff in the fermions. So the first one of the Qn series is the vector charge. The second one is the axial charge. All of these operators commute with the Hamiltonian. And together, they generate an algebra that was first used in Onsager's 1944 paper, and was henceforth known as the Onsager algebra. And this is it. This is the algebra these two operators generate. All right. Now, coming back to Andreas' question, he asked, the TB Majorana lattice translation symmetry is a Z symmetry on the lattice. When I define my axial charge, I take TB to the first power. But why not take it to the third power, to the seventh power, to the 13th power, to any odd power? What operator do I get? Well, you will get this Qn with an odd n. So, in fact, all these operators, for finite n, so you take this Qn with finite n, when n is even, it goes to the vector charge, whereas when n is odd, it goes to the axial charge. So we have not only one axial charge on the lattice, but we have many of them. Gn is the commutator between QB and QA, and you can show that it goes to 0 in the continuum limit. Very good. So as you take the commutators, eventually n will become order L. They are conserved operator on the lattice, but they are highly non-local. It's a good operator, but it acts non-locally on the fermions. It is what it is. All right. So we spent a lot of time talking about this axial charge that has quantized eigenvalue, but it doesn't commute with the vector charge. We spent a lot of time trying to find whether in the literature people have talked about this. And after a while, we found this paper by Thacker 30 years ago, which mentioned this charge very, very briefly at the end of the paper. That paper had 2 citations when we found it. Now it has 3. And both citations were self-citations. So this was really a paper by all definition was forgotten in the literature. Now you could have asked, what if I really want an axial charge that does commute with the vector charge? Well, in fact, there is such a symmetry. So there's a different conserved quantity, which we call Q tilde A. That was already discussed in this paper by Tom et al. In the 70s. It commutes with the vector charge, but it does not have quantized eigenvalue. And both of them flow through the axial charge in the continuum limit, but we don't seem to have a lattice axial charge that is both quantized and commutes with the vector charge. Well, you might think, Arco, Sal, and I, we're just a bunch of amateur kids. And suppose someone from the audience who is an expert think about this harder, maybe they will be able to find yet another, say, Q double tilde A, that both commutes with the vector charge and has integer quantized eigenvalues. But in fact, that's not the case. If you have a quantized charge that commutes with the vector symmetry, that would have violated the no-go theorem by Kapustin and Sopenko. So this is really the best you can do. Let me quickly say that you can ask, what are the consequences of these 2 symmetries? We show that any Hamiltonian that commutes with the lattice vector and axial symmetry QB and QA is necessarily gapless. So this is very reminiscent of the consequence of a perturbative to Hoof anomaly of continuous global symmetry in quantum field theory. And this comment was also made in Anna's talk. So our vector and axial symmetry rule out any gap scenarios and leave the gapless scenario as the only option. This is a snapshot of a phase diagram. So there are infinitely many terms you can add to the Hamiltonian while preserving both the vector and axial symmetry. They are all gapless. We take a 2-dimensional slice, and you get some interesting phase diagram. Okay, I won't have time to talk about this. But the backstory is that we actually found this axial symmetry in the free fermion system guided by a non-invertible symmetry in a closely related system that's called the XX model. So the summary is that take this simple Hamiltonian. In addition to the manifest U1 vector symmetry, the lattice Hamiltonian has an exact axial U1 symmetry too. Both U1 vector and U1 axial are unbroken on the lattice. However, they don't commute and generate the Onsager algebra. The Schwinger anomaly of the continuum free Dirac fermion field theory arises from this interesting non-abelian Onsager algebra, and this provides a novel mechanism for anomaly matching. In the continuum, you have two commuting U1 with a Schwinger anomaly. On the lattice, the generators of these two continuum symmetries are exactly preserved on the lattice. But on the lattice, it's hard to tell whether there's an anomaly or not. Instead, there's a complicated non-abelian algebra. I don't know if I should say they have an anomaly on the lattice or not, but at the very least, we proved that they have similar consequences as an anomaly, meaning that they enforce the low energy phase to be gapless. There are several outlook directions to better understand the relation to Nielsen dinomia and to realize more general chiral symmetries. And of course, the obvious question, can we generalize to 3+1d? Now, this is where my slides end before yesterday. But last night on Archive, there was an interesting paper by Joya and Ryan Thorngren, where they generalized our story to 3+1d. So they consider a single Dirac fermion in 3+1d and consider a lattice Hamiltonian realization of this theory. The single Dirac fermion in 3+1d has a U2 flavor symmetry. They realized, and it has a SU2 subgroup, and they found that this SU2 subgroup also arises from the same Onsager algebra. Now, in our story, there's a Schwinger anomaly for the U1 vector times U1 axial. In their story, in 3+1d, the SU2 flavor symmetry famously has a Witten anomaly. So I'm running out of the time, but this is the final slide. In our story, Schwinger's anomaly arises from the Onsager algebra on the lattice, but in their story, Witten's anomaly arises from Onsager's algebra. And with that, same algebra.
Generalizations of the Onsager algebra?
Well, Saul and I are working on that, so stay tuned.
Say how something indexed by a single integer shows up in a 3+1 theory. Sounds 1+1 dimensions.
Right. So that's an excellent point. I don't understand. Okay, let me say how it works in their story. So they also have a manifest vector charge symmetry, vector U1 symmetry on the lattice. So that's called Q0. Now, what they found is that they constructed another Q, which they call Q1. And the defining property of Onsager's algebra is that starting from Q0 and Q1, as you take the nested commutator, you get the entire thing. So from that algebraic point of view, you get the entire Onsager algebra. But you're asking an excellent question. What physically does that little n mean? And I don't know, and the reason I don't know is because last night I didn't have a chance to read through their new paper because I went to see the SpaceX launch with you yesterday. But I would like to understand more about their story. All right, with that, thank you for your attention.
Okay, so we had part of the discussion during the talk, but we have time for a few questions. Oh boy, there's a lot. Let me start with Igor and then start moving around.
Yeah, thanks for a great talk. In hindsight, we scheduled it at a good time in the conference. But just a comment on Schwinger anomaly, like you had the slide on the Schwinger anomaly in the Schwinger model, like an early slide, right?
Yeah.
Like,
Yes.
Yeah, I would say that there have been several talks on this mass shift in the Schwinger model, but by Ross Dempsey and Grisha and Etsuka. And I would say that we exactly realize the rotation by pi over 2, the axial rotation by pi over 2 as a unit shift, the usual unit shift. And that causes the shift of theta by pi, which is exactly the... So just some subgroup of this axial Schwinger anomaly, I think, is possible.
I totally agree. In fact, in my previous slides, I did put the... I think it would be interesting to further understand what's the relation between our U1 axial to the mass shift formula that you guys have. And Ross and I, we've been thinking a little bit about it, and we hope to make more progress.
Yeah, in our case, we just make the usual Dirac shift, like both Majorana's shift under this unit lattice string. And then definitely theta shifts by pi. And
Okay. Okay, I see a question in the back, and let me run.
Yeah, very nice talk. A lot of these charges remind me of how one computes extended charges or L0, L0 bar and conformal field theories with the boost operator. So you can probably generate all these charges also by acting with the boost operator.
Well, which boost operator do you have? You mean like in CFT?
Like in CFT, yes. I mean, these are CFTs, and the boost operator will be the local Hamiltonian. Since you have a decomposition of two Hamiltonians, you just act with one. So there's two Virasoro's that you can...
So that's in the continuum, right? On the lattice...
even on the lattice. On the lattice, you can use the boost operator and generate that way the other charges. And then I think you can generate... all these shifts by n are generated by the boost operator, so...
All this shift by n is generated by this TB, right? This Majorana lattice translation will take you from...
It's also generated by the boost operator.
Okay, I would love to understand the relation better.
Since you're here, do you get anything interesting if instead of considering commutators, you consider just products?
Interesting question, but I don't think we found anything interesting because in the continuum, what would you say? In the continuum, right, I don't think I ever multiply QV with QA together. I mean, it gives you some operator that's conserved, but when you exponentiate it, it probably won't act nicely on the local operator. So I think that's one thing about what's nice about our axial charge is that it really acts locally on the lattice fermion. And if you start doing something weird about it, you might eventually ruin the locality.
So building on that, what about gauging? And can you build an effective description of the 3-4-5 model?
Excellent question. Well, but Steve, I really, the way I understand it, there are two questions. Yeah. So first, can we gauge any of these U1 symmetries? And we did that in the paper. I just didn't have time to talk about it. So for the U1 vector symmetry, you can gauge it, and that's exactly what Tom did in the 70s. What about our U1 A, this axial charge? And as I said, a related question is that why do I care whether the charge is quantized or not? Well, one reason I care is the following. When the charge is quantized, I can couple it to a compact U1 gauge field. So this guy, we can gauge, and we did gauge it, and you get a new kind of lattice chiral gauge theory. But maybe the interesting question you can further ask is, when you gauge U1A, what happens to U1V? Where's the, in the continuum, we know it should disappear. On the lattice, when you gauge U1A, indeed U1V also disappear, and vice versa. But the way it works on the lattice is different from the way it works in the continuum. The way it works on the lattice is because they don't commute. So when you impose the Gauss's law for one of them, the other doesn't commute with it, so it's automatically broken. This is also one reason. So here on this slide, I present the quantized charge and the unquantized charge kind of on the same footing. And I didn't say I prefer either one of them. But if you really ask me privately, I would say that I probably like the left one better because it has quantized eigenvalues, it can be gauged, whereas and it also acts locally on the fermion. Whereas this one, you cannot gauge it, and when you act on a local fermion at site J, it will spread out over the entire chain. So that's the question that's the answer to your first question. Regarding your second question, can you get more general chiral symmetry like the 3-4-5-0 model? 3-4-5-0 symmetry. For that one, you can get an unquantized charge for the 3450 symmetry, but we don't know how to get a quantized version of that. And that was done in a follow-up paper from a month ago, this paper.
So why can't you just take
Good. What's the problem? Right. So if you want to get a 3450 symmetry or more general chiral symmetry, you will have to take linear combination of the vector charge and the axial charge. But the QV and QA, while individually they have quantized eigenvalues, because they don't commute, the moment you take linear combination, the sum of these two operators will not have quantized eigenvalues anymore. So we are able to get some conserved quantity on the lattice that flow to the 3450 charge. It's just that this lattice conserved operator does not have quantized eigenvalue. Is that good or bad? I think that's up for you to decide.
Just one also comment. So Alexi and I wrote down a lattice discretization of like a bosonized version of the 3450 model, but with the infinite dimensional Hilbert space.
With Evan Berkowitz.
Yeah, and Evan. Got to mention Evan. So my question, it goes a little bit beyond your talk, but from what I remember from the paper, the argument that this theory is gapless, I mean, sort of trying to use the symmetries, you actually had to look at deformation, like look at the space of symmetric deformations of the Hamiltonian. Do you think that there's some more general argument that basically just takes the Onsager algebra, more like how we use anomalies in the continuum?
Good question. The short answer is I don't know.
I remember there were a couple of questions near the front here. Okay.
There are some non-abelian algebras that we know how to gauge.
Like SU2?
Yeah. So, beyond the fact that there are infinite many generators, how do you see that the Onsager algebra can't be gauged?
Well, so yeah, good question. The reason that I don't know, I personally don't know how to gauge the Onsager algebra is actually related to David's earlier question, that the Onsager algebra contains all these QNs. And when n is older L, it's a highly, and you exponentiate it, it's a highly non-local symmetry. And generally, I don't know how to gauge something that's non-local. So it's not so much about the non-abelian nature, it's more about the locality nature. You see, it's interesting that you start with QV, that's completely on-site. And then you add to the story QA, that's still quite local, just nearest neighbor coupling. But then as you take commutator, you get more and more non-local things.
Maybe last question.
Besides TB, there's also RB maybe that reflects just the B guys. Does that do anything interesting?
Very good, very good. Yeah, so in fact, Sal, Arco, and another student at MIT were working on generalizing this story to include all crystalline symmetry of the lattice model and do conjugation on the vector symmetry. But for reflection, you see, one thing is that the resulting operator generally might not act locally in position space. And lattice translation, in a way, acts better.
One last question.
I wonder, this Onsager operators, I just wonder whether you can find out some continuum analog of it, because it doesn't look like they one form, but it could be some reflection of this, right? And this is what I wonder about.
You're wondering, what is there a continuum counterpart? That's an excellent question. You see here, what do we say? We say that take this operator G, take the continuum limit, it goes to 0. This we check. You check all the matrix element goes to 0 as you take the continuum limit. And therefore, in that limit, all the Q's collapse to 2 of them, and G goes to 0. That sounds like a very, very boring limit. Having said that, there might be a way to scale this operator. For instance, maybe you can multiply it by some power of L and take the limit, and that will probably give you some non-trivial conserved operator in the continuum. We don't know what that would give us. That's an interesting question. My guess is that this theory flows to free Dirac fermions, so there's a huge chiral algebra. So maybe they are related to the chiral algebra of a free Dirac fermion, but we haven't analyzed that.
Okay, thanks.
All right, let's thank Shu Heng again and go get coffee.